Dr. Abhinav Deshpande. Dr. Abhinav Deshpande is IQIM, that is Institute for Quantum Information and Matter, postdoctoral scholar, research associate in theoretical physics, California Institute of Technology, Pasadena. He obtained his PhD degree in physics from University of Maryland, USA. He did his master's from IIT Kanpur. He worked as research assistant in the Department of Physics at University of Maryland, USA. He invited as a visiting scientist to many reputed institutes like Max Planck Institute for Quantum Optics, Munich, and Institute for Quantum Information and Matter, California Institute of Technology, Pasadena, and to many other such kind of institutes. He has many research publications in reputed international journal and conferences. He is a recipient of many awards and fellowships such as NSF Travel Grant to attend Quantum Information Processing, Dean's Fellowship from the Graduate School of University of Maryland, General Proficiency Medal in IIT Kanpur, Academic Excellence Award in IIT Kanpur, and many more. He delivered many expert talks at various academic events and conferences. He is an editor of Quantum Journal and reviewer of many reputed conferences and journals. He has also written many press articles on quantum computing. His research interests include complexity theory and applications to many body physics, classical simulation of quantum systems, and quantum dynamics. We welcome you, sir. Now I request you to start the session, please. Over to you, sir.
Thank you so much. That was a very kind introduction. It's a great pleasure to be here, and thank you all for coming. And yeah, the title of my talk is as follows: Am I living in the post-quantum advantage era? So this concerns a particular milestone called quantum advantage, which is also known as quantum supremacy in quantum computing. And we'll get into that shortly. But before that, I want to say a few things about Caltech and myself. But yeah, feel free to, at any point in the talk, just ask me questions. I think you can just post them in the chat and maybe it's moderated. Anyway, yeah, the more interactive it is, the more enjoyable it will be for everyone involved. Yeah, so the California Institute of Technology is located in Pasadena, just outside of Los Angeles. It's a kind of smallish campus, relatively speaking, but it has a huge impact. And the Institute for Quantum Information and Matter, called IQIM, is a center at Caltech, and it has around 30 faculty working in quantum information and adjacent areas. And these faculty come from various departments such as physics, computer science, chemistry, mathematics, and some branches of engineering as well. And yeah, this is one of the buildings where IQIM is partly located, and this is where I work. Yeah, so coming to my work, I'm mostly interested in the field of computational complexity theory and what it tells us about physics, particularly many body physics and quantum physics. So some of the questions I ask on a daily basis are, what problems can or cannot be solved using quantum or classical computers? And by classical computers, I mean just non-quantum, the regular computers that we use. Yeah, and by asking questions like this, we hopefully learn the answer to this other question, which is, what are some of the features of problems that allow us to solve them on quantum computers easily? And more generally, I like looking at the boundary between classical and quantum computing. Okay, yeah, so if you'd like some an overview of quantum computing, there's a talk of mine on YouTube which can be found here. You can just email me later if you want precise links to anything. I also have another talk on what is known as complexity phase diagrams, which describes my PhD research. But yeah, today I'll be talking about this field called quantum computational advantage. So, okay, let's jump into what this means. This is a demonstration of some well-defined computational task that can be solved by a quantum computer much faster than, say, a classical one. Okay, and here's a meme from my favorite meme page, so there's a quantum computer that's depicted and looking at like a huge array of supercomputers. And yeah, it turns out that the supercomputers need to do a lot of work just to mimic a fraction of the power of a quantum computer. So this is the broad goal in this field. Okay, and yeah, I should be more precise as to what I mean by dramatically faster. This is usually quantified through asymptotics, which means you look at several instances of the problem, all varying in size, and you look at how much time it takes to solve larger and larger instances of the problem and how it scales as a function of system size. Typically in computer science, we say that if something only takes polynomial effort to solve as the system size increases, then it's sort of easy. But if something scales much worse, such as exponential, then we usually call that hard. So that is what I mean by something that's easy on a quantum computer and hard on a classical computer. Okay, but there's another issue that comes up, which is that experiments and our physical world is necessarily finite size. So this can never perfectly witness asymptotics. So we can never give like a watertight proof that something is scaling this way based on empirical data. So in practice, we also need to show that classically one cannot do much better than whatever algorithm one is applying to solve a particular problem. Okay, so these are some issues that come up when we talk about this particular milestone. Okay, and yeah, as I said earlier, this is also known as quantum supremacy in the community, but that word has largely fallen out of favor. Okay, so one of the tasks for showing a quantum advantage is this task of approximate sampling. And that is studied through this Boson sampling problem, where we have the following setup. So we have a description that's given to us of a linear optical circuit, U, which acts on, say, M modes and some initial Fock state that looks like this. Okay, all this means is that there's one photon going into this mode. There's no photon going here and here. And there are two photons going here and so on. So we apply this linear optical interferometer and we measure how many photons come out at the end. Okay, and so the output distribution, it's a complicated distribution on all possible arrangements of, say, 4 photons in this picture into 6 modes. Okay, some modes can contain 0 photons. Okay, so there are combinatorially many output patterns that you can have. And what you have essentially is a distribution that is supported on this complicated pattern. Okay, so what we want to do is just sample from that distribution. And in practice, we would like to allow for the algorithm to make some error, and that's quantified this way. So if du is the ideal distribution that would have resulted by sending in photons to this linear optical circuit, and do is the distribution that the algorithm samples from, then the distance metric we are using is called the total variation distance, which is defined like this. So you sum over all possible outcomes, x, times the absolute value of the difference between the two probabilities that are assigned by the two distributions. Okay. So yeah, this task is believed to be classically hard. And this is what Scott Aronson and Alex Arkhipov showed back in 2011. So they gave very strong complexity theoretic evidence for this, for the hardness of this task. And essentially the way it goes is that you assume that this task is easy. So it's a proof by contradiction in some sense. So you assume that there is an efficient classical sampler for this problem. And then that leads you to like a long chain of implications. And then ultimately bad things happen. I won't go into what exactly the bad things are. But it's broadly similar like to a statement like this, that it is sharply hard to compute output probabilities of random linear optical circuits to some small additive error. Okay, so this is the implication of there being an efficient classical sampler. And then the rest of the task is to argue that, this is impossible. Sorry, I mean, it is impossible to solve, to compute these things in any reasonable time. And then, yeah, these techniques, I mean, the reductions given by Aronson and Arkhipov have also been ported into other architectures. Some of these are the IQP model, so that consists of commuting gates. There's also something called the one clean qubit model. And then there's a very physics-based example called the 2D icing model. And there's also random circuit sampling, which by far is the most popular, I would say. So let's go into random circuit sampling. The idea is you have, yeah, can you see this part of my screen over here?
Yes, sir.
Okay, thanks. Yeah, the idea is you have a circuit here acting on qubits, and these gates are, say, random. They're just random. And so you have 1 qubit gates and 2 qubit gates, which are denoted through this. And I've shown this in 1D, but you can also think of 2D or other architectures. So yeah, you just apply like a deep enough circuit, and then you just measure at the end. And then that again is sampling from some complicated distribution. Now the support of the distribution is of size 2 to the n, if you have n individual qubits here. So this was a theory proposal by Boson et al. That first surfaced in 2016. And the asymptotic hardness was studied by Pula and et al. In this paper. Okay, so that's the task. But let's discuss another issue that dogs these proposals, and that is that of verifying the output. So it turns out that, yeah, like the problem at hand is that we are only getting samples from the distribution, but we don't know how likely those samples are. And if you want to, so the obvious way to measure how likely the samples are is to just take a lot of them and then see how often they occurred. But that is not a good strategy because there are too many outcomes. So we'd have to, in general, take exponentially many samples before we can do the naive thing of computing the output probabilities. So that's not an efficient way. And it turns out that there's no sample efficient way to verify that you are indeed getting samples from some target distribution. So is there some alternative? There was one proposal, again by Boson et al., to get around this. And that was the following. So you just take some M samples from the device. Let's label them X1 through XM. So each of these are bit strings. And what you would do is classically compute their ideal output probabilities. Now, this step is something that also requires exponential resources. But at least it's different slightly from the earlier proposal in the sense that the number of samples we need is still polynomial. It's just that we have to do a lot of exponential computing on say a supercomputer, right? Not necessarily on a quantum computer. And right now it's cheaper to do things on supercomputers than on quantum computers. Okay, so you do this, and then you compute the score called linear cross entropy benchmarking score, which is just given this way. It's essentially something like a dot product between the ideal probabilities and the empirical probabilities. Okay. And yeah, so the task is to score high with respect to this linear XCB score. And it turns out that for random circuits, the output probabilities have a shape that looks very much like this. And this is called the Porter-Thomas distribution. So on average, in some interval here for P between P is the ideal output probability for say P and P plus DP, the number of bit strings with probabilities in that interval goes like this. So why am I telling you this? It turns out that if you know this Porter-Thomas distribution shape, you can also compute the linear XCB score. So if you have an ideal random quantum circuit and you are perfectly producing samples from that output distribution, then on expectation, the linear XCB score would be 1. And it also turns out that if you're instead sampling completely at random, you have no idea which bit string is more likely than which other bit string, then that would give you a score of 0. Okay, so that's why it's like a nice measure, and people think it reflects the actual quantum fidelity. Any questions here? I can pause for a few minutes.
Any queries from the participants? Oh, I think there are no queries.
Okay, sure. Okay, so what does scoring high on this linear XCB test mean? So this task was sample efficient by construction because we just took a few samples M and we computed the classical probabilities. Oh, can you elaborate on the quantum fidelity? Yeah, the quantum fidelity is a measure that tracks how similar two quantum states are. And formally, it's just given by the dot product in Hilbert space, and on this modulus square of the dot product of the two vectors in Hilbert space. And yeah, so it's 1 if you are looking at the same state, and 0 if you are looking at two orthogonal states. Thank you for that question. One or one many. I don't understand what that means.
So the answer that you have given with respect to that only, depending on the states, she is asking.
It is 1 to 1 or 1 to many.
Oh, so yeah, it's defined between two states. Yeah, so it's 1 to 1. Yeah. Okay, thank you. Yeah. So this linear XCB test was by design sample efficient. And the task is now different from before because all we have to do is score well on this test. Okay, and like another caveat is that we need the samples to be uncorrelated. And this is okay. I'll use this shorthand. See the signal for this mouthful phrase of scoring well on this linear XCB test with sufficiently many uncorrelated samples. It'll just be useful later on. And okay, one thing I'd like to underscore is that scoring high on this test is not like does not equate to doing well on the original approximate sampling task. Okay, so it's just a modified task. And that means that we need new complexity theoretic evidence that this task is hard because we have changed the goalpost. Okay, and this is what, to some extent, Anson and Chen and Anson and Gunn did. They looked at the hardness of scoring well on this linear XCB test. And in particular, they made an extremely strong conjecture in my view, which is that any score on this test that's strictly larger than 0 is asymptotically hard for classical computers. And what I mean by larger than 0 is that as the system size scales, the score remains constant. The score like doesn't go to 0 as your problem size increases. Okay. Yeah, and just to give you a bit more of intuition for why they thought that this test is also hard, they show that scoring well on the linear XCB test is almost as hard as computing output probabilities with any small improvement over random guessing. And the intuition is that for a random quantum circuit, it scrambles things so much that you have no idea whether a given bit string is going to have probability, larger or smaller than 1/2 to the n, for example. 1/2 to the n is like the average output probability because there are 2 to the n bit strings in total. And yeah, this is saying that doing anything better than guessing just uniformly at random is already hard. Okay, there's a question or maybe a comment. The notation 2, number of photons used by you, overlaps on the qubit notation. 2 denotes the value place. For the purpose of that slide, yeah, the notation I used was just number of photons. Yeah, nothing to do with qubits. Okay. Yeah, so let's come to Google's experiment and what they did. So in October 2019, this was huge news, and it made the front page of Nature, and it also went to like many other media outlets. So Google claims that it has achieved this task of quantum supremacy, and what they claimed was it's a task that would take the most powerful supercomputer on Earth 10,000 years to do, but it only took a few minutes for the quantum machine. So we are now in a position to discuss exactly what Google did. What they did was they achieved a score on this linear XCB test of 0.002, which essentially means that their quantum computer was outputting noise 99.8% of the time and some signal 0.2% of the time. And then, yeah, they took 1 million samples, which took 200 seconds. Yeah, and they said that classically it would take you 10,000 years to do that. But it turns out that this classical runtime has since been improved a lot by other groups and researchers. So this task only takes 15 hours now on the best supercomputer. So this begs the question whether what Google did was asymptotically, so to say, quantum supreme. So if we are discussing an ideal noiseless experiment, then the answer is yes, because random circuit sampling has pretty good evidence that it is hard. And moreover, this evidence that I presented you earlier by Anson and Gunn and Anson and Chen of scoring high on the linear XCB test also applies. But when we talk about a noisy experiment, which is what we usually get in nature so far, it turns out that the fidelity and the score on this linear XCB test both decay exponentially as the system size increases. So this is sort of problematic, and that's illustrated here. So with a deeper circuit, the score on the linear XCB test dropped exponentially. And yeah, this is a log scale. So the entire hardness claim rests on the fact that this error bar doesn't go all the way down to 0. Or in other words, this B is 0.002 up to some standard deviation, which is sort of less than the original score. And that's important. So yeah, you may ask whether it's asymptotically hard to do well on this linear XCB test when B also decays exponentially. So notice that this is not a problem if B is some tiny constant, but it's constant as the system size increases. It's only a problem because Anson and Chen and Anson and Gunn showed that this is hard. But if B is also decreasing exponentially, then it's not quite clear. Okay, but you may still argue that this is still evidence for the exponentiality of Hilbert space. Okay. Or in other words, the noise is making the signal harder to see. But this means that we have seen the signal. Okay. And that means that, Hilbert space is large, which is what we wanted to prove in the first place. Okay. Yeah, let me go ahead. So yeah, one popular interpretation of this was that it was as momentous as the Wright brothers' first flight at Kitty Hawk. Yeah, my view is that asymptotics are only a guide and the real world is always finite. So that means that so what matters is how much time it takes for like a real classical computer. And it's still true that today's best classical algorithms are nowhere near what Sycamore does. And Sycamore, is the name of Google's chip that achieved this task. So again, I'd like to hammer in this meme, which is that you still need a lot of computing power just to mimic a fraction of what the quantum computer is doing. And yeah, this is a developing story. And yeah, the rest of the talk is going to look at what happened in the aftermath of Google's exciting, result and announcement. Okay, so the first few developments that happened were attacks on Google's claim, such as there was one by IBM where they said that if you used a different algorithm instead, where you hypothetically used up all the disk space that is available, then it would take a mere 2.5 days as opposed to 10,000 years. But more relevant, to this discussion was a paper by Pan and Zhang, where they gave a pretty fast algorithm, but that outputs correlated samples. It took 5 days, but it was actually done, unlike this earlier suggestion. They further improved upon this and gave an algorithm that also gives uncorrelated samples. So this is better. And moreover, it took only 15 hours. And Scott Aronson, who's a pretty famous blogger in quantum computing, talked about this too. Okay, so what are the remedies if you are on the side of quantum computing and you would like to see quantum computers do better than classical? One is obviously to go to higher qubit numbers and build deeper circuits with better fidelity. So that's so as a theorist, it's easy to say to the experimentalist, you should just do a better job. But that's also a fallback thing that you should only say when you have nothing else to do. Then actually this is what the next generation of quantum advantage experiments are doing. So there was one development in December 2020 with photons in the group of Jianwei Pan. They also, in the same group, also exhibited a quantum advantage with superconducting qubits, just like Google. Finally, they used Gaussian boson sampling as well with phase programmability. And they again improved on the superconducting quantum processor and they used 60 qubits instead of 53 and with 24 cycles instead of 20. And because things grow exponentially, 60 is much more powerful than 53. So for example, this is their benchmark. So it turns out that with this 60 qubit 24 cycle device, even getting a fidelity of 0.03% would take something like 48,000 years. And this is with the revised estimates where, say where the Google experiment originally would take now 16 days as opposed to 10,000 years. Okay, so there are constant developments both on the algorithm side and on the experimental side. And this is like an arms race now. So at some point, would you say, well, one can ask the question whether this race is still interesting? And I would say, it depends on how you look at it. If the claim of quantum advantage depends on particular constants, then obviously yes. Because that's similar to, so going back to our Wright brothers plane analogy, that's similar to planes getting better and better. And in real life, we care about constants. So if this is, for example, a history of the original few planes. Okay, but if we switch gears and just think about asymptotics, like, can we also talk about whether this task is asymptotically hard or not? So in this regard, there was a team from Google that sort of did an attack against the boson sampling experiment that I just mentioned here. It was this one, I believe. So what they did essentially was sample from a distribution with better total variation distance than the experiment itself did. Okay, so if you recall what I said earlier, that in practice, you will never be sampling from the correct distribution, and you'll always make some error. So Google theoretically made smaller error than the experiment itself. And the the way they did that was to use the fact that lower order correlations in fact dominate the distribution, and it's enough to get these right. And experimentally, what happened was the experiment got the first few orders slightly wrong. And even though it was getting the higher order correlations more accurately than, say, Google could, that never made up for the total variation distance that was lost. Yeah, like, so there are some imperfections and the experiment cannot catch up afterwards. So yeah, Scott Aronson, who was the one who actually gave Hardness results originally for the total variation distance metric, said that that is not some hallowed measure, and one can substitute that with anything that's sensitive to the higher order correlations. And to some extent, so if your response is that we are changing goalposts again, to some extent that is what Google also did originally, because they went from approximate sampling to this other task of scoring high on this linear XCB test. So there have been more asymptotic attacks recently. There was this work by Gao et al., for example, where they look at random circuit sampling and give a classical algorithm, which they claim has better asymptotic performance. So for example, this is from their paper. They have an algorithm that partitions the qubits into non-interacting blobs. And they look at the mean XCB score, the cross entropy benchmarking score, with the algorithm and with realistic noise. And their main argument is that if you look at this figure, for example, this yellow line seems to be going down, whereas this blue line is roughly constant. And then if you extrapolate, then at some point they'll intersect and the blue line will be better. So the classical algorithm will be doing better than, say, the extrapolated experimental curve. But yeah, there's a paper of mine, and along with my co-authors, which seems to indicate that this sort of behavior of the yellow line will not go on forever, in the sense that yeah, if you increase the number of qubits, but you fix the depth of the circuit, then at some point this yellow line will become horizontal again. So that means that, yeah, we don't know whether this blue curve, which is the score achieved by the algorithm, whether that can intersect this or not. Okay, so yeah, I think we need better asymptotic theory. And this is what Boolan et al. And Kondo et al. Recently did. So if you recall earlier, I said that we need to show this statement that it's sharply hard to compute output probabilities of, say, random circuits to some small additive error. We can't yet prove that statement, but we can prove that statement where we replace this by extremely small additive error. And yeah, if you're interested in knowing what that precisely means, you can, yeah, just look at this paper or this paper. So okay, like, this still does not unconditionally prove that approximate sampling is hard, but we are pretty close. And one interesting thing in this paper by Boolan et al. Is the following. They show, interestingly, that if you have a noisy circuit instead, then that also retains some signal of hardness. So it means that they essentially ended up showing that output probabilities of noisy circuits are still hard to approximate if it's some small enough error. So in practice, it's extremely small additive error. But on the other hand, it's also clear that noisy random circuits are not hard to sample from approximately. And that's because the output distribution gets exponentially close to the uniform. So it converges pretty quickly. So, the classical algorithm can simply just sample from the uniform distribution and be good enough. So, this is why we need better theory. Ideally, we'd like a different task or a different distance measure such that the whole thing is still quantumly easy to perform even with noise. Our existing linear XCB score does not satisfy this because quantumly the score decays exponentially when we have noise. We'd also like good evidence that it's classically hard. Ideally, as good evidence as, say, the hardness of approximate sampling. And then another really nice feature would be, verifiability. So you should be able to verify in polynomial time whether the task was achieved or not. Okay, that brings me to the summary. So the task of what I call seeing the signal is quantumly hard. I mean, it's hard to do in our real world. So this means that there's no exponential advantage that we see yet. But again, I'd like to remind you that this signal is exponentially hard to see, but we have seen it. We have done a lot of effort to see it. And that's already evidence of the exponentiality of Hilbert space. And when one is not considering asymptotics, then doing larger and larger experiments and trying to show that it's secure against better and better classical algorithms would increase our confidence in the claim that quantum advantage has been achieved. And in my view, this is only a transitionary era now, where you see this race between classical and quantum algorithms and exhibitions of advantage, but it'll soon be won overwhelmingly by quantum computers. And for that, we need error correction, which is going to be the real game changer in this field. Okay, that was it. Thank you so much. I can take any questions.
Any queries from the participants? Any queries?
You may write your queries in the chat box.
Chat box. Yes. Tanveer Alam raised the hand. Kindly ask the question. Ma'am, can you unmute him?
Just 1 minute, I'll unmute him. Who wanted to ask?
Tanveer Alam was the person.
Tanveer Alam, just a minute. I'm not able to locate. Yes.
Tarang Jain also raised the hand, ma'am. Tarang Jain.
Okay, Tanveer Alam, you can ask your query.
And Tarang Jain also, ma'am, raised hand.
Just let him ask first.
Okay.
Mr. Tanveer, you can unmute yourself and ask the query. Okay, the other one was
Tarang Jain, ma'am.
Tarang.
Tarang Jain.
Okay, just a minute. Let me see. Hmm.
One query is in the chat box, sir. Abhinav, sir.
Okay. What does exponentiality of a Hilbert space mean? Oh, sorry if I wasn't clear. What I mean is when you increase the number of qubits, let's say you have an n qubit system, then the state of such a system is described by a vector in a complex 2 to the n dimensional vector space. And that's also a Hilbert space. So what I mean by exponentiality is just the scaling of 2 to the n versus n. Yeah. So if you just add 1 qubit, you effectively double the number of, effectively double the dimension of Hilbert space.
Any other queries from the participants?
Tarang, you can ask.
Yeah. A very good morning to all of you. I have a general query. Am I
Okay.
audible?
Yeah.
Yeah.
So I want to know whether we can execute these quantum computing algorithms on Jupyter using the simple hardware we have, or we need some extra hardware for doing so.
Oh, yeah, you can certainly simulate certain quantum algorithms on your regular laptop. But the only issue is that we are currently inhibited by the fact that it takes exponential effort to simulate a quantum system. So, for example, I guess most people on like laptops can do say up to 20, 24 qubits. So if you have a question, or like if you have an algorithm that can be simulated on something with less than that many qubits, then yeah, you can see on your laptop how well it works, for example.
Actually, I have written an algorithm and I tried to execute it not using quantum computing, but general algorithm using Python. And it executed only twice. After that, it came out of range. Error was there. So I was thinking whether I will be able to execute that program by making some changes in that using quantum computing. So what do you say? Will it be possible for me to do that?
Is it a quantum algorithm?
It's a basically general algorithm of calculations. Some multiplications are there, but it's going to be out of range. A big number is there, so exponentiation is there. So my general computer is not able to calculate that.
Oh, okay. Unfortunately, today's quantum computers are not yet at the stage where we can replace a classical computer or something as good as your laptop at anything. So yeah, it depends on the exact problem you want to solve. And yeah, I should say that quantum computing is not like a one size fits all solution. You have to tailor them to the problem that you want to solve, and only some problems might be sped up with quantum computing.
So I have to try myself. R&D will be there, and then I will be able to get whether I'm getting something or not.
If you can phrase your problem, like make it well defined, and I guess identify what the bottleneck of your algorithm is, that where you're running into this sort of memory error, right? Maybe there's some use case that quantum computing can be good at.
It's only number system. I am working on general number system, you may see, and some large calculations are there. Multiplication of big numbers is there, and it has to be done again and again and again. But using my normal computer, I am able to do it only twice. So I have to do it, you may say, thousands times. So, but I am not able to do that because my system is not able to.
Wow. Okay.
Work on that.
Yeah.
Okay, thank you.
Sure.
One more query is there, sir, in the chat box.
Okay. It's not quantum simulation to be technically correct. No classical machine can really simulate something quantum. Yeah, what classical systems do is a kind of matrix multiplication, but collapse and measurement does not happen. Yeah, sure. I mean, this is more of splitting hairs. Like I argue that, yeah, like anything you can do digitally is still a valid simulation. Yeah, some people use quantum simulation in another sense in which you speak about. But if you look at what like the English meaning of simulate means, which is just to mimic something else, then this is perfectly valid.
So the problem is there itself, that you cannot mimic the measurement, neither you can mimic the correlation. So you can use the sparsity of the matrix and go for matrix multiplication and see that where the circuit final state is. But when the advantage will come, that will come for the measurement, and there you are not going to get the advantage. So this kind of simulation is not really quantum simulation.
No, I did not mean that.
No, what I wanted to say,
simulation
because there was a question from the participant and whether she can simulate in her laptop or not. So she can see certain features, but it will not going to be simulation. That will not going to give any time advantage. Means that advantage will not come unless
that was
already.
I was not under the impression, that the participant wanted something that was, looking at something advantageous. Yeah, like, but essentially, if you don't care about efficiency, then quantum computing can be.
No, I just added the comment to make it tighter, so that the new participants don't carry something wrong impression that you can make it faster by using that.
Any other queries from the participants, please? Thank you, Abhinav sir, providing us deep insights into the quantum computational advantage. Thank you, sir. Thank you very much, sir.
Oh, thank you so much
for sparing out the valuable time and sharing your knowledge, sir.
Sure. I have added my email address in the chat in case anyone has questions. You can just feel free to reach out.
Okay, thank you, sir.
Thank you, Dr. Abhinav, for sparing your valuable time.
Yes, thank you so much.
Thank you.
Yeah, see you.
So this is the end of our first session of the second day. So we will have a short break and we will join our next session at 11:15. So kindly be present at 11:15. Devi Priya ma'am. Good morning, ma'am. Are you there, ma'am? Good morning, ma'am. Am I audible to ma'am? Am I audible, ma'am? You are, ma'am, asked to unmute. Okay. Let me give you the permission, sir, ma'am. Okay.
एक सेकेंड 2-3 मिनट 11-20 पे कर गुड मॉर्निंग डॉक्टर देवप्रिया Dr. Devipriya, can you hear me? You can unmute yourselves. Dr. Devipriya, you can share your screen. We cannot, we can try out. Everything is going fine. Hello, ma'am. How are you?
Fine, ma'am. Fine. Can you hear me?
Yeah, we can hear
Yeah.
you.
Okay. But still, I cannot share my screen.
But you are given the rights. You are a host.
Yes, ma'am. But
You are on laptop.
yes, ma'am. Laptop.
So can you, you can click on the share screen symbol that is there in the bottom.
Yes, ma'am. If I click on that, it says host disabled participant screen sharing.
Or just give me a few minutes.
Okay.
एक मिनट मैं उनको बोलती हूँ और Dr. Devipriya, can you share the message that you are getting?
Ma'am, you want me to share the presentation to you?
Message.
You just try out to share, otherwise you can send it to us. We will start.
Still, it is disabled.
Login from 2 devices, ma'am.
You have login from 2 devices.
No, ma'am. Only from my laptop.
Ma'am, we have two Devipriya in participant list.
Okay, one is Devpriya. She is DEVI.
Ma'am, so the confusion is Devpriya is co-host and Devipriya is not the co-host.
Oh, 1 minute. Okay. Just a minute. Okay. Ma'am, please try now.
Okay.
By
Yes,
mistake, I made her host.
Yes, ma'am. I'm able to do that.
Okay.
Is it visible?
Yes, it's successful. Okay, we can start the session. Yeah.
Okay, ma'am. So, hello everyone. Welcome to session 2 of the second day. The speaker for our second session is Dr. R. Devipriya. Dr. R. Devipriya is a professor in the Department of Artificial Intelligence and Data Science at KPR Institute of Engineering and Technology, Coimbatore. She obtained her PhD degree from Anna University, Chennai in 2013. She has more than 15 years of teaching and research experience. Currently, she is guiding 8 PhD scholars, in which one scholar has submitted the thesis. She has done many consultancy projects and has an international collaboration with Machine Intelligence Research Lab, USA. She authored many articles in the reputed journals and conferences. She is an active editor, reviewer, and advisory member of many journals and conferences. She has also organized many workshops, FTPs, training and seminars. She is a recipient of many awards such as CTS Best Faculty Awards, Best Faculty Award, Best Outgoing Student Award, and many more. She has also authored books on Java programming and system software. Her research interests are artificial intelligence, data science, and optimization techniques. We welcome you, ma'am. I request you to start the session, please. Over to you, ma'am.
Thank you, ma'am. Thank you for your introduction.
Thank you, ma'am.
And I hope good morning, everybody. So I think from yesterday, you might have heard about what is quantum computer, what is quantum computing, and what are the essentials of quantum computing. Now in this session, we are just going to see what are different applications of quantum computing. So even though this is a new topic for most of us, and this is going to rule the world in tomorrow. So that's what we are going to see different kinds of applications now. And even though it is far from commercially scalable, but more than mere fantasy, quantum computing will one day be a transformative reality. So if we see quantum computing now, in today's date, it is far from commercially scalable. It is not commercially available and it is not common in the market. But it is not something which is not going to happen. It will definitely happen in near future and it will be a transformative reality. We are going to see how this quantum computing is going to transform our entire day-to-day life. And the father of quantum physics, Max Planck, has once said that when you change the way you look at things, the things you look at change. So when there are some things in front of us, we have different perspectives. I may see the same thing in one perspective and you may see the same thing at different perspective. And the third person, he may see in different perspective. So when we change the way we are looking at things, obviously the things which we are looking at will definitely change. That is the principle behind quantum physics. And that was the statement given by Max Planck. And what is quantum world? I think you have all got a glimpse of all these things, but let me just give you the basic idea of what is a quantum world and start with different kinds of applications. Data is recorded and stored in a different way. We all know that how data is stored. Maybe initially it was stored in relational database or some structured format, but later it has become an unstructured format where we have our data stored in different kinds of formats, heterogeneous formats, like it may be in text, audio, video, and it may be stored in the form of bits. Usually the bits will be the bottommost atomic level of unit or data that is stored. But here in quantum world, through non-binary qubits of information, we store data. Rather than binary bits of zeros and ones, we store our data through non-binary qubits of information. That is, it reflects the multiplicity of states in the quantum world. It's like fuzzy, where if we are having a 0 or 1, then that has a proper meaning. That 0 means it's not available and 1 means it's present. So absence or presence of something. So it's just being represented by binary bits. For example, if we are using a fuzzy logic or something, so in between 0 and 1, there were many values. For example, if you take the values 0 and 1, you have only 2 values. But there are so many values in between zeros and ones. For example, 0.1 to 0.9 and 0.0.1. 1 to 0.11112. Likewise, there are so many values available in between this just 0 and 1. But actually, we don't bother about that minor differences. But when we are talking about how the data is stored, it has a major implication. It has critical importance. And that's why when we have small amount of data, that's not going to matter. But if we have huge amount of data with terabytes and gigabytes of data, and if we need to process all those data, definitely that will be a huge task, and our computational complexity, our performance, our operation performance, execution time, memory consumption, response time, everything has to be optimized. This can be optimized only with the help of data storage at a proper level. And here, 0 to 1 contains multiple states, and this multiplicity enables faster and lower cost calculation for combinatorial arithmetic. For example, if we have so many data, for example, if we have n number of customers, for example, if we have millions of customers for a bank usually a nationalized or internationalized bank usually have so many customers, millions of customers will be there. And I want to search for the customer who has the highest transaction. So how can I do that? Obviously, I have to search for so many millions of customers. This is not a simple task. This is a very huge computationally complex task, which cannot be done using normal algorithms or techniques. So in such situations, quantum computing comes into picture, and that's going to change the entire world of computation. And as you might have known, it's not bits. We call this as qubits, quantum computing bits. So it also scales exponentially. Quantum computers is capable of scaling exponentially. So we can store and process huge amount of data. Initially, we may start with a small amount of data, but rather at later point of time, we can just increase the size of our data input exponentially. But here we are increasing and dealing only in terms of qubits and not years. For example, in this slide itself, you can see, so just 0 or 1, but instead of that, we just have so many data. So where we have different range of values that each one indicating a separate importance. So if this is the case, if this is our bit, it has some importance. And if this one particular qubit has changed, it has something different meaning. It has something different else to convey. So this is how qubits are working. And from this example here, we can see that a bit can be either 0 or 1 in a normal traditional computing process. Whereas in qubit, so superpositions can be represented anywhere on a sphere. Suppose if this is the range of values between 0 and 1, you can represent any point between these 0 and 1 with the help of qubits. And that's where the power of quantum computers lies. And see, this is another example to just demonstrate you how these classical bits and qubits differ from each other. So this is a case where 0 and 1 are represented where either presence or absence. Whereas in this case, we have qubit. So this is just represented as a sphere where in between this range, we have the radius, and this is usually represented by this. The qubits are usually represented like this. A slash followed by 0 or 1, and then you have this arrow mark like this, where this represents the radius of the sphere. That means there are some range of values associated with this. So that is the meaning of this. And this is the standard formula for representing qubits. And here, when you have so many possibilities, for example, if you are trying to find out if you have, for example, if a thief is going to steal something in a supermarket. Usually the supermarket contains, for example, thousands of items in the store. And if he wants to select some items which are highly beneficial to him, that means which gives him maximum profit. There are, for example, there are 10,000 items in the store. He cannot evaluate the combination of all 10,000 items. So that is very much difficult. Even if you are doing this with the help of classical traditional computing systems, trying the best combination out of 2 power 10,000 combinations or possible permutations will be very much difficult. So in this case, we have 1 out of 2 power. If we have n number of bits, obviously we have to choose the best one out of 2 power n possible permutation or combinations. That's very much difficult. And if we are using this quantum bit, we can explore all of 2 power n possible permutations. So that is why we are able to achieve the highly desired result with the help of quantum computing. See here, if we have 2 power n bits, so they are all represented with the help of qubits, and we can evaluate that in less time. We can evaluate or complete that process in lesser execution time and with minimum amount of memory than traditional computing. This is why people are moving to quantum computing. But again, this is not so much easy. So this is again a difficult task, since so much complexities are involved, so much formulas, so many things are involved here. And we have 2 important things which are commonly dealt with quantum computing. These 2 things actually revolve around this quantum computing. First one is superposition. It's nothing but if we have a quantum system. For example, if we are using a quantum computer, every quantum computer or system should have the ability to be in multiple states at the same time. So that means something can be here and there or up and down at the same time. At the same time, it should be present. For example, if you like a movie or not. So we usually say, if we like the movie, 1. If we don't like, it's 0. But if we like the movie to some extent, it can be somewhere between 0 and 1, or it can be somewhere between 0 to 0.5, and again between 0.3 to 3.5. So likewise, it can be somewhere here and there, up and down at the same time. That means in the sphere of that quantum qubit, we can move that multiple states. We can have multiple states at the same time. That's why it can be, okay, I like that movie to some extent, but I don't like the movie in some perspective or some extent. That's how the superposition can be represented. And we have something called as entanglement, where there exists extremely strong correlation. There exists strong correlation between quantum particles, and that is so strong that 2 or more quantum particles can be linked in perfect unison. Suppose if we have 2, or for example, I have 5 quantum particles which are somehow linked and they have some strong correlation, but they are physically apart. Even when they are placed at opposite ends of the universe, the relationship or the bonding or correlationship between them can be properly established. For example, if I'm here and my son or daughter or my husband who is extremely close to me, maybe at opposite end of the universe, maybe at Australia, I may be at India, I may be in India, and my husband or my son may be in Australia. Even though we are at opposite ends of the universe, but there exists a strong correlation between us, and those kind of relationship between the quantum particles can be established perfectly. The only thing is that we have to establish proper mechanism of correlation. That's it. So that is called as entanglement. And seemingly impossible connection inspired Einstein. So even Einstein was inspired by this, and he described this word entanglement as spooky action at a distance. Even at a far off distance or unimaginable distance, you can establish relationship. Even people or they are saying that treating people from remote distances, like your acupuncture or acu touch. So even people or patient can be at a remote location, maybe somewhere at US or UK, and the doctor may be at US or UK, and the patient may be at India or even Africa, or it can be anything. So even that kind of thoughts, the travel of thoughts and connectivity can be established. So only the thing is that we have to establish proper mechanism and route or mechanism to devise that. That's it. And that's the power of quantum computing. And there are some advantages over classical computers. So using quantum computers, we can encode more information. So why I'm saying all these advantages is that whenever we are thinking of applications of quantum computers, when you explicitly need these kind of advantages, you can go for quantum computers. Otherwise, if it is not that much required, we can process the same thing with classical computers. So these are the explicit advantages of quantum computers, And when you are in demand of all these things, you can go for quantum computers. And when the first advantage is that it encodes more information. Quantum computers is capable of encoding more information. That's why when you have an application where you need to process huge amount of data at the same time, then you can go for that. For example, share market data, stock market. So in the stock market data, even at every second or millisecond, we need to process huge amount of millions of data. So that is very dynamically changing data. So in such kind of situation, you can go for quantum computers. And when you need some powerful, extremely powerful mechanism to process your data, then you can go for this, because quantum computing are extremely powerful in terms of all memory consumption, usage, and again, it poses some complexity also. The storage capacity, everything has to be compromised. Only if you explicitly need all these things, you can plan for quantum computers, and it is massively parallel. And when your application is so small, then you need not go for this quantum computers. If it is extremely large, and if something need to be done in parallel, if there are so many processes, and if all the process need to be done so parallelly, so that you need to combine all your results, then you can go for quantum computers. And it easily cracks secret codes. And when there is a need for strong encryption and decryption, cyber security kind of applications, you can go for quantum computers, because if you are encrypting your data using a strong encryption algorithm, this quantum computers can easily crack those secret codes with the help of powerful security algorithms. And it is extremely fast in searching databases. If you have huge amount of database with 1 TB of data or 2 TBs of data, again, it is very simple. Just imagine a case where if you have for example, if we are searching for something in Google search engine, actually that search engine contains huge amount of TBs and GBs of data. We all know that how much extensive storage space Google search engine has. But again, when we are searching for something, and we are searching for just the keyword quantum computers in Google, it just returns the result in no time. So how this is possible? Google computers use this quantum computing. They all use Google, IBM. So there are so many companies which are exclusively using this quantum computing. Only then they can provide fast and accurate results in this time. And there is when there is a situation that hard computational problems become tractable. And we all know that there are, whatever may be the problem, we can track or we can classify that problem as tractable problems or intractable problems. Where tractable problems means we can achieve solution or we can solve that problem.
Ma'am,
Somebody, ma'am? Ma'am, am I audible?
No, yeah, now you're audible.
Till now, I was not audible, ma'am.
No, just for a few seconds. Just for a few seconds.
Maybe
Okay,
network issue may be there, ma'am.
Okay, ma'am. Okay. So just do I need to repeat advantages of classical computers? No.
No, ma'am, it's okay. Within second, your network recovered.
Okay. Okay. So there are two types of problems, usually tractable and intractable problems. Tractable means some problems can be solved in polynomial time and we can attain solution. Whereas for some intractable problems, we may not know what is the exact solution, or we may not know what is the solution. And solving those kind of computational problems are extremely hard, and that cannot be handled usually by traditional computing facilities or the traditional algorithms. In such cases, we can go for quantum computing, where we can solve even these intractable problems with some reasonable amount of time and complexity. And there are so many applications, but to start with, I'm just showing you some common applications which we are commonly using in our day-to-day life. And then later, after just discussing all these common applications with the help of scenarios, I'll just explain. And after that, we'll go for some other applications. First application is production line optimization with quantum computing. Then we have portfolio management with quantum algorithms. fault detection, and optimizing transport scheduling for railways. These are common applications which we normally see in our day-to-day life. If these kinds of problems are solved by using traditional computers, we can achieve some solution that may not be optimal always. For some cases, it may be optimal. And for some cases, if it is extremely difficult or hard, definitely that will be a complex task. And we can easily solve those problems with the help of quantum computers. Let us explore these common cases. Rather than just listing out all the applications, I'll just explain few applications with some scenarios, and then we'll go further. And the first case is portfolio management. We have already discussed how difficult it is to manage a stock market. And if I am a user, if I am a stock market investor and I want to select the right investment portfolio, even I'm investing my stock, I'm an investor for more than 15 years in the stock market. But usually, whoever may be, we may feel difficult in identifying the right portfolio. When the stock market, the price, the exchange rates go high or up, we may not know what happens. Even during that COVID pandemic period, initially the stock market, the Bombay Stock Exchange or NSE, the rate was something different. And all of a sudden, the entire situation changes. And we might have invested with the assumption or with the conclusion that if we buy these kind of stocks and if my portfolio contains these kinds of stocks, definitely that will give you benefit in some, for example, in 5 years of time, this much amount of profit I will get. But this is not an easy task. So it may varies from person to person. I may find some set of items or some set of companies as good companies in my portfolio. You may find it something else. And the third person, again, he may find it some portfolio. But what is the right investment portfolio? So this is not a simple test because we have to analyze all the companies. For example, if I'm planning to buy a share of retail industry, then I have to list out all the retail industries so that are in market and all the quarterly results, recent quarterly results of all those companies. And then I have to analyze and I have to choose the right combination. I want to make a combination again. I have to buy 2 companies from retail industries, 2 from pharmaceutical industries, 2 from agricultural industries, 2 from cosmetics. Like me, there are so many things. I have to choose the right thing. That's again a great task. So suppose if there is a scenario like whatever may be the financial sector, and again, these are recurrent challenges. So one day this may be a situation, and in another day, again, you may face a downtrend in your market. Again, you have to change your decision. So you need to maximize the profits obtainable from each portfolio in line with the rules and objectives. Again, my constraint will be something else, and yours will be something else. So for each and every person, the algorithm or your advisor, your technical advisor should be able to suggest you good combination of portfolio. So, and the challenge here is that whenever there is a large amount of investment portfolio and it takes extensively long processing times in traditional computers. So whereas if you are using quantum optimization algorithm, we can do this with the help of weighted maximum independence set. That is all possible with the help of quantum optimization algorithm. I hope since you are all faculty, so you might be familiar with all the optimization algorithms. Yes, ma'am. So, sir, any response?
Yes, ma'am. Yes, ma'am.
Okay, so we all know that we are trying to bring out the best result out of all the combinations. So that's where there are some optimization algorithms which are exclusively suitable for quantum computing, and we can use those optimization algorithms to make a right or optimal investment portfolio. And when we are doing that, it can speed up the processing of selection. So, and again, by combining existing techniques, we can easily perform calculation that would otherwise require long processing time. And again, the second application, optimizing trains. Consider how big our Indian railway system is. So if the Indian Railways wants to schedule trains at different railway stations, for example, Delhi, Mumbai, Chennai, so Coimbatore, there are so many trains. And there are so many trains, there are so many platforms available in each station. and there will be so many train departure times, arrival times, there will be so many operations, and everything has to be calculated and processed. Scheduling of railway mechanism system even at a particular single station is even a difficult. Imagine how difficult it will be for the Indian Railways to optimize all the trains with proper and proper train schedules. So planning, that's again a big challenge. And again, this kind of optimization can be done using something called as train platforming problem. This problem is usually called as train platforming problem, and even this kind of difficult problem can be solved by using quantum computing. And see, in this case, the benefits of quantum computing in handling this problem is that we can handle extremely huge number of combinatorial variables with substantially shorter processing times. Why this quantum computing are extensively used in hard complex problem means, in complex problems, there will be huge number of variables associated. Highly combinatorial variables are associated, and even then, in addition to the number of variables, there will be there will be high correlation and complex correlation exists between the variables. We have to represent all those relationships, the variables and the complexity or relationship between the variables also. So that is where quantum computers can be applied. And when we are doing that, the managers or whoever is in charge of that system can optimize the entire railway station network by significantly reducing the impact of any delays. So even the software delays, when we are searching for something in the Indian Railways website or whatever may be, that delays can be reduced, and all the delays in physical railway stations can be reduced with better service quality. This is another application where we can detect faults. It is highly used in cyber securities and also fault detection. We know that neural networks are commonly used, and deep neural networks. We know that neural networks, deep learning algorithms are mainly based on neural networks, entirely based on neural networks, and we can train any deep neural network with the help of quantum computing. We have already moved from machine learning algorithms to deep learning algorithms with the intention of achieving more accuracy, right? So when we train our machine learning algorithms to the next level and extensively, then we call that as deep learning. So that deep learning with extensive learning capability can be done with the help of quantum computing stage, where we can easily detect faults in products coming from a production line. So whatever may be the production unit, for example, if you are manufacturing a car, or you are manufacturing chocolate or watch or anything, you just imagine manufacturing of any product. So that product will be manufactured in some sequence, and if there is any fault in any of the particular sequence, the entire process will go wrong. So we need to identify the faults initially. So that fault detection can be easily done with quantum computing. So see this scenario, the detection of defects and faults with production lines is often crucial in preventing customer dissatisfaction. Even when we are manufacturing 1 meter of cloth, so if there is a small thread coming out of the cloth in between, then the customer may get dissatisfied. Even this may cause huge crores of loss to the manufacturer. So that kind of things should be avoided. Avoiding damage, even the lines, the production lines may be damaged sometimes, and that can be done effectively. Image processing and machine learning techniques that enable quality control require a highly accurate system of classification. And in such cases, we can use quantum computing, where deep learning algorithms are combined with quantum computers. And if there is image processing algorithm, for example, if there is a production line going in between, where it is in operation, and if something is gone wrong, I can easily identify, okay, this is the place where some fault has occurred, and I should rectify that problem. That kind of extensive monitoring of faults can be done with the help of quantum computers in allied with this deep learning algorithms. And neural networks created using quantum algorithms are usually called as quantum neural networks. They are shortly called as QNNs. That is quantum neural network structure which are created using our quantum algorithms. They are substantially faster than traditional neural networks. And when we are designing this neural network with the aid of computing, quantum computing stage, it is capable of identifying false at a high accurate rate. These are the common scenarios that we have seen, but now we are going to see what are other applications, common applications. We can think of any application in AI field. When we are having huge number of applications, obviously it will be a difficult task. It will be a challenging task to match with the accuracy and speed. For example, if you are running a machine learning algorithm, for example, optimization algorithm, nature-inspired algorithm, it may run for hours and days. For example, if you are running a genetic algorithm for an application with some huge amount of data, it may run for even 2 days or 3 days to get the best solution, optimal solution. But that is not practically desirable. So we need solution in no time. So whenever we are implementing a machine learning algorithm and in any AI task, so when there is an increase in number of applications, increase in number of data or devices, whatever may be, definitely quantum computing can be used. It helps in processing through complex problems in very less time, which would be done with huge time and huge computational complexity with traditional computers. That means we can use quantum algorithms in all places where AI and machine learning algorithms are used. We can integrate these things. Next, computational chemistry. So now we have recently come across the situation of COVID, where we have people all over the world were trying to find the medicine for COVID situation. So how the right medicine or how the right maybe vaccine or medicine is identified, how it is formulated. So when you have so many chemicals available in chemistry lab, so we do not know exactly which combination of chemicals or medicines will provide you the solution or remedy for this particular disease. So they have to try out huge combinations. And again, practically trying out all different combinations of chemicals for finding out the right vaccine or medicine is extremely a difficult task. That is why quantum computers can be used. For number of quantum states, we have huge number of quantum states. That means even in a tiniest of molecule, we have number of quantum states, and that will be very difficult for normal computing systems to process. But whereas if you are using quantum computers, where instead of both just 0 and 1, we can have huge number of values, a range of values between 0 and 1. That will give you immense power to the machine to properly and successfully and accurately map the molecules, which opens the way for right vaccine or medicine. And again, these quantum computers have a huge application and opportunity in pharmaceutical research, where even if a particular molecule, even if a drop of molecule and even minute molecule of medicine is added a bit extra, or if it is deficient, the entire treatment can go wrong. So it is very critical, and even at the cost of lives of human beings or any other thing. So it has to be very accurate, and quantum computers can be extensively used in computational chemistry. And applications, for example, these are some of the applications, even improving the nitrogen fixation process for creating ammonia-based fertilizer. Suppose if an agro-based fertilizer company is trying to design ammonia-based fertilizer, and it wants to fix the amount of nitrogen. So that will be best suited for producing the right thing for a particular plant. For example, apple tree or tomato plant or whatever may be the thing, the right amount of fertilizer and chemicals have to be identified. And creating a room temperature superconductor. So again, every minute and second, the room temperature may be changing. So that has to be appropriately dynamically changed. And removing carbon dioxide for a better climate. We all know that in today's world, there is huge pollution, where we live in a world with full of carbon and carbon dioxide, carbon monoxide around us. That creates so many diseases in human beings. suppose if a company, or if I want to remove a particular level of carbon dioxide and I want to provide pollution-free environment, so what kind of treatment I can give to the environment? So that can be thought of, and that is the place where quantum computers can be used, and creating solid state batteries. So these are some of the applications. You can think of any application like this, where whenever we need the right combination of chemical molecules or physics, even in physics. So quantum computing is nothing but physics. Actually, quantum physics is the base thing, and only from the quantum physics, quantum computing and all those things have evolved. So in even all combinations of chemicals and chemistries, we can use quantum computing. And drug design and development. So as we have seen in the previous slide, we can design the drugs. Usually drugs are being developed via trial and error method. Nobody knows. So this drug will be better for this particular symptom. Even when we are going to the doctor with a small headache or fever, they may not know exactly what is the problem. They based on the symptoms that we are seeing, that we patients tell the doctors, and even from their own experience, the doctor might prescribe you some medicine or drug with the assumption that this medicine might cure the patient. And again, that's also a trial and error thing. He is not accurately, he won't say that accurately this medicine will treat, will give complete cure. So he usually says that, okay, just try this medicine for 3 to 4 days. And even if the fever is not reduced, you come back to me after 4 days. So likewise, so the drugs are usually given to the patients with trial and error, and even think of the situation where how critical developing such drugs will be. And developing such drugs with so many expensive materials, raw materials, is not easy. It is very expensive and also risky and challenging. So we have to think of all the complexities, and in such situations where making a trial on all drugs or all drug combination is difficult, we can go for quantum computing. So researchers believe that quantum computing can be an effective way of understanding the drugs and its reactions on humans. Before making a trial on humans, we can use quantum computing to identify this will be the effect for this particular combination of drugs. So which in can turn, save a ton of money and time for drug companies. That is why Dr. Reddy's labs or somebody or many pharmaceutical companies have come up with so many vaccines, and even some vaccines have turned out to be successful, and some have side effects, some have turned out to be unsuccessful. So why all this has happened? And even at huge cost, they have made a try. And if quantum computing can be used in such kind of experiments, we can save amount to some extent, and it enhances efficiency of the drug design dramatically by allowing companies to carry out more drug discoveries to uncover new medical treatments. So that is again possible. And cyber security and cryptography. Imagine a case if I'm having a password for my mail and my friend wants to crack that password. It's a very difficult task. So if I have 15 characters in my password, he has to try out so many combinations. Practically finding out all these combinations is a difficult one. But how can we done this? How can we do this, complete this? If I want to encrypt my password so that nobody should crack my password, right? So with our increasing dependency on digitization, we are more vulnerable to threats. So there are so many hackers trying to steal all your data, even in Gmail or whatever may be the mail or Facebook, WhatsApp, we have sensitive data. So in today's modern world, we have no way other than storing our data in digital form. And whenever we are storing in digital form, obviously that will be stored in a server, cloud server, where so many people will be watching our data. Even if I'm sitting in Coimbatore or in Chennai or Mumbai, people will be watching all my actions at US or UK. So I have to secure my data. Even if I'm opening some application in my mobile phone, somebody else will be watching that I'm opening mail now, I'm opening WhatsApp now. So I have to provide proper encryption, and that can be done. And quantum computing with the help of machine learning algorithms. Quantum computing itself alone cannot do this. We can combine this algorithm with other machine learning and deep learning algorithms in to protect our data from cybersecurity threats. And it can help in creating encryption also. And this is commonly called as quantum cryptography. When quantum algorithms are used in cryptographic algorithms, then this is called as quantum cryptography. And this has huge application because we have to try out different combinations to encrypt our passwords, right? And financial modeling, for a finance industry to find the right mix for fruitful investments. And again, there are so many risks associated. There are so many factors which need to be considered, and all these things have to be analyzed. For example, if you're using Monte Carlo simulations, I hope you all know Monte Carlo simulations, where if I want to make a financial investment, for example, in share market, so I may not simply invest. Okay, so the previous day, the share value of this particular company A is 1,000 rupees. So today it might increase. I cannot invest like this. So I have to watch the pattern of previous history. For example, okay, yesterday it was the share, and the day before yesterday, what was the share amount? And last week, for example, if I'm watching the market on Monday, I have to find, okay, last Monday, what was the scenario? And if this is the first Monday of the particular month, okay, previous month, first Monday, what was the rate? What was the share market value? And what was the previous year's value? What was the previous 3 years value? What was the previous 5 years value? So likewise, I have to analyze all the previous histories. That means n instances of values have to be analyzed, and only then I can invest, so that I can safely invest my money. So such kind of cases, we can use Monte Carlo simulations. In other ways, we can call, technically, we can call it as MCMC, Monte Carlo Markov chain. So this can be done, if they are done using conventional computers, it consumes huge amount of time. But when we apply quantum technology to perform all these operations, definitely the companies, investments, financial companies can provide better solutions. And algorithmic trading is another potential application. So where, whenever we are making some trading, so we can use this traditional computing algorithms, where machine learning uses complex algorithms to automatically trigger share dealings. So when I'm scheduling, okay, so tomorrow at 11 o'clock, this share should be bought. So I can schedule my share dealing, share purchase and sellings, everything can be done. If there are high volumes of transactions, again, manually, I cannot sit and buy and sell. So I will usually, what obviously will do, I will schedule all the share market transactions, and that should be done. That can be easily done using quantum algorithms. Logistic optimization is another important application scenario, where we can transport our goods from one place to another place, from within the country or across the countries. For example, if I'm using an imported Rolls-Royce car in Chennai, so that includes a lot of logistics. The car might have been manufactured in US or UK or China or Hong Kong, or it may be in somewhere else, and that has to be transported from that particular manufacturing unit to the local harbor or airport or whatever it may be, and that has to pass through so many ports and stations. So, and if a company, logistic company, wants to do all those things, it should have extensive computing capacity. So, for suppose if industries wants to optimize their logistics and scheduling workflows, then supply chain management. So it is all associated with supply chain management, right? So there will be, for example, if the manufacturing unit of Honda is at Hong Kong, it has to transport its products to so many countries across the globe. It has to transport its cars and all those things. So imagine how difficult it will be for the company to transport all those things and schedule all those things. So, right. So the operating models need to continuously calculate and recalculate. Sometimes we might have calculated and we might have scheduled something at later point of time. Maybe after half an hour, it has to recalculate something, and it has to change the route. It has to find the optimal route of traffic management, how much traffic it will be in fleet operations, who will be handling all those things, air traffic control. So what kind of air situation is this, freight and distribution. So all those things, climatic conditions, all those things have to be considered, and then finally the decision has to be made. And two common quantum approaches that can be used to solve such kind of problems are called as quantum annealing and universal quantum computers. Quantum annealing is nothing but it's an advanced optimization technique. We all might have heard simulated annealing in machine learning. It's an algorithm. It's an algorithm to produce the best result, optimal result. Similarly, it's an optimization technique in accordance with simulated annealing. It is expected to surpass traditional computers. And in contrast, universal quantum computers are capable of solving all types of computational problems which are not yet commercially available. Most of the quantum computing solutions are not available in the market. They are under research, and more products are yet to be developed. So this is just the starting era, and we have a long way to go. Weather forecasting is another application where we include several variables to consider, such as air pressure, temperature, air density. And so all those parameters need to be considered to predict weather and to broadcast, okay, for tomorrow, you should not go to shipping or something like that. So there are so many variables involved in making the proper decision. And with quantum computers, meteorologists usually do this. They make decisions, they forecast weather with the help of all those things, which will provide greater insight to climate change and ways to mitigate that. And future of quantum computing. So there are so many publicly funded high performance computing centers, which are initially taking up the quantum computing. IQM, a Finland-based quantum computer company, it has found that 27% of HPC centers worldwide were experimenting with quantum computing. So initially it was very low, and now recently many companies have started using quantum computing, and this is again increasing, and it has predicted that 76% of public funded companies will be using quantum computing by 2023. Imagine how complex our data complexity will be, and there will be a need of highly extensive computing capacity, and quantum computer can satisfy those kind of situations. As a full stack provider, it builds and assembles quantum computers. Quantum computers are not just simple computers, they are just a full stack. So where it includes all the capacities and capabilities, it should process all kinds of data at all levels. It should handle all heterogeneous data, and all the computing capabilities need to be supplied with this full stack. And quantum computers are capable of doing all those things. IQM will need supply chain resilience along with the infrastructure that produces chipsets and software for the machines. This IQM quantum based company, so it is involved in developing quantum systems and software. And now let us see how many companies are using quantum computing. So initially IBM was using quantum computing, and even so many applications in IBM, they are using quantum computing. Microsoft is using quantum computing, Google, JP Morgan shares, Airbus, Hitachi, Huawei. There are so many companies. This is just a few list of few companies. And now let us, even though so many companies are using quantum computers, let us see some computers and specific applications of those companies. Rigetti Computing, the director of quantum startup, it's a startup for quantum computers, and he's among those who have indicated that quantum computing's method of simultaneous calculation will likely be successful in analyzing the very, very complex system of variables that is weather. So the director of Rigetti Computing, he once said that simultaneous calculation needs to be done in some scenarios. For example, in weather forecasting, simultaneously we have to monitor air pressure, temperature, moisture content. Everything has to be done simultaneously at different geographical locations. Suppose if there is a cyclone which is being developed at Mumbai, that will travel along Mumbai to maybe South India or maybe to North India or Northeast or Southeast. We have to simultaneously calculate everything. So that kind of complex variable analysis can be done using quantum systems. And cyber security post-quantum is another company which implements quantum computing for establishing cyber security. And Protein Cure is another biotech startup where they are using quantum computers for developing many drugs. Pharmaceutical drugs are being developed using this biotech startup. So these are some forms. And Daimler Truck AG is another company which is a German car manufacturer, and it's the parent of Mercedes-Benz. This company is also utilizing this quantum computing for logistics, because they have to manufacture the car and they have to transport all the products to the right destination at right time. So this can be done only with the help of extensive scheduling. If scheduling of one thing or one particular task has gone wrong, obviously everything at the next step will be collapsed. So it has to be done perfectly. And Volkswagen AG. So you all know that Volkswagen is an automobile car manufacturing company, and they all use, again, even this can be used in production line. If a car is being manufactured, or if a bus or truck is being manufactured, imagine how difficult it will be, how complex the structure will be. If a door has to be fixed, if a door, or if a nut or bolt, or if a mirror or clutch, brake, whatever it may be a small minute thing, or it may be a large thing like your engine or motor. So there are so many things, complexities involved in that, and everything can be handled with the help of quantum computing algorithms. And IonQ is another company. So, and it has released so many quantum solutions, and as of 2022, it has released Forte, its newest generation of quantum systems, and it allows software configurability and flexibility for researchers and other users. So it promotes climatic change solutions. So it suggests that there will be huge climate change in our entire globe, and that climate change can be predicted initially, and all those changes can be handled dynamically with the help of quantum solutions. So that means in weather forecasting and handling of pollution, even the pollution control can be done with the help of quantum computing, as we have already seen the level of chemicals or the level of fertilizers, everything can be monitored and they can be controlled. Right mix of all those chemicals can be controlled with the help of our quantum algorithms. And Cold Quanta is another company where they use cold atom quantum computing, in which laser cooled atoms can act the role as qubits. So we all know that, again, what is a qubit, right? So the bits which contain the values, different range of values between zeros and ones. And again, we use something called as atom quantum computing. So this is very minute molecule, and this company uses this. With this method, fragile atoms can be kept cold. We all know that, again, atom or space research or atomic research is a huge thing where we need to concentrate very minutely, and fragile, highly fragile atoms can be kept cold. When the temperature of that atom is not maintained properly, obviously that can create a huge blast. So we should be very careful enough in maintaining proper right temperature for those kind of atoms, right? So this operating system remains at room temperature, allow quantum devices to be used in various environments. So since these quantum systems can be very effectively used for maintaining this kind of sensitive information, they can be extensively used. And these are some of the materials or newspaper cuttings or something, news releases. So allocation of railway traffic with QBO. QBO is a solution. So where Reply is a company, so which is extensively involved in developing quantum solutions. So this is the application that we have seen already, right? Scheduling of railway system. So if we have many platforms and many trains coming out at different times, they are arriving at different times, they are departing at different times, the tracks, railway tracks, everything has to be changed dynamically. So coordinating routing trains in railway station is a well-known and complex problem, and given so many conditions are involved in that. And suddenly, all of a sudden, there may be some unforeseen events. If there is a change of track, or if there is a damage in the railway track, obviously everything will be changed. So using the QBO model, Reply, this company has demonstrated how optimization of railway traffic management system can be done and improving the end user experience. And again, this is another application, the best ally for last mile optimization. Again, Reply has taken full advantage of quantum computing, creating a quantum inspired algorithm for last mile optimization. So it again includes all these things. And NL is another application where it enhances the efficiency of maintenance work with quantum inspired algorithms. So it is this company NL is involved in electricity and renewable energy production sector. So and again, maintaining right amount of electricity supply chain management again. So the proper amount of electricity needs to be generated. The demand should be estimated prior, and based on the demand, sufficient electricity should be generated in right units. And after generation of power or electricity, it may be a renewable energy or non-renewable energy, whatever it may be, the source of energy, it has to be generated sufficiently at the unit, and it has to be distributed through proper transformers. And again, scheduling of transformers, everything is a very critical task, and that can be done effectively using quantum inspired algorithms. And the scope of quantum computing. So to what extent we can use? It can be useful for scientists for conducting virtual experiments. So suppose if a scientist at a lab, it may be an R&D lab, it may be a pharmaceutical lab, or it may be a physics lab, or it may be a chemistry lab, or even it may be a computer lab. It will be very difficult to conduct experiments physically. And that kind of virtual experiments can be done easily by using quantum computers, where we can exactly predict if we are mixing this particular combination of atoms or inputs or chemicals. So what will be the result? This is very extensively used in atomic research. So we can model the behavior of atoms and particles at unusual conditions. So even Abdul Kalam, so Dr. Abdul Kalam, so he has done so many atomic research, and they have explored many things, many atom bombs and all those things. And practically exploring bombs at different locations is a very risky thing. And we cannot do all those things. We cannot experiment with atoms and bombs. So what the alternate option is, we have to first analyze the behavior of all the atoms and particles, even all the minute amount of chemicals, the right proportion of chemicals, and what will be the reaction. Everything has to be initially modeled, and after analyzing the reaction of all the process of all the formula, then we can go for actual implementation. In such situations, scientists can very well use these quantum computing for conducting virtual experiments. And imagine another case where we have huge amount of data. For example, if we have a phone book with 1 million phone numbers, and I want to search for a number. If I want to search a number, it will be a very extensive task. Imagine how difficult it will be. So suppose if the number I'm searching for is at the millionth position. So I have to go through all searching steps. I have to search and compare my searching number with all the remaining numbers. So this is not an easy task. In 1996 itself, Lou Grover from Bell Laboratories, he has discovered that using quantum computer, we can search for a number in 1 million phone number with just 1,000 steps. If I'm doing with traditional computer, I have to cross through 1 million steps to find whether the particular number has existed in that phone number list or not. But I can do the same thing with 1,000 steps using quantum computers. Imagine how efficient it will be. And different implications to the development of human civilization. So if we are developing so many quantum computers, so how that impacts the human civilization? People can produce goods at much lower cost. That means they are nothing but advantages. So how these quantum computers are going to change our future? So people can produce goods at much lower cost because the R&D process occurs in a virtual lab. So for example, if I want to design a car, practically designing a car is very much difficult, and it's also expensive. I cannot do everything physically. Suppose if I'm able to do that in a virtual lab, and if I'm able to visualize everything virtually, and then after conclusion, after fixing, okay, this is the right model. After fixing the model, if I'm practically implementing, then that will be much cost extensive. So we can use those kind of things, and the amount of time to create urgent innovations is cut short. For example, if there is an urgent need for COVID medicine or vaccine, nobody was prepared for that. So that was an emergency situation, and there was a need for urgent innovation. So what can we do? We have only limited amount of time. Within short period of time, we have to develop a vaccine so that people could be saved. Otherwise, this disease will spread so fast that so many human lives will be lost. So this is an urgent situation, and there is a need for urgent innovation. We have only limited time. In such situation, we can use quantum algorithms to develop and make trials with different combinations, with huge number of combinations, and we can develop solutions. And another thing, before manufacturing items, the developers can detect their failures also. Suppose if there is a development or in a production unit, if there is a development of a particular product in production unit, and they can priorly detect the failures. Okay, if this temperature, or if the motor is running with this particular speed, this can cause failure at this particular line. So likewise, the possible failures can also be predicted before, and they can work on solutions. Manufacturing process will become more sustainable and environment friendly. Since we are not going to develop or design, we are not going to develop the product physically, we are just going to model everything virtually, and only after finalizing everything, we are going for physical development. So that can be very beneficial, and we can have a sustainable manufacturing industry, and it will be environment friendly also. If we are making trials, we will destroy the environments. We need to produce more harm to the environment by developing so many hardware components. That is of no use. So we can save our environment from pollution also. These kind of benefits are also added. And even though there are so many advantages which exist in quantum computers, there are some challenges too. These qubits are still difficult to translate into arbitrary values. Okay, so if we are using traditional computers, we can easily say, okay, this is 0 and 1. 0 has this much value and 1 has this much value. But whereas if qubits are used, 0.0001 is different from 0.1000. But how you are going to differentiate between the impact of these two values? So, and how these arbitrary values are translated. If you are choosing some arbitrary values are nothing but random values. So how these arbitrary values are generated, how these values are analyzed, how they are stored, how they are processed, how two different arbitrary values are taken into consideration, and how they should be analyzed, how they should be reported again. So how the result of handling all these arbitrary values should be produced as outputs. So these, again, handling of qubits are a little bit difficult. Even now, researchers are struggling with handling of qubits. There are still more scope for finding or developing right combination or right representation of qubits. That means representation of qubits and translation of qubits are a little bit difficult. And if people, if the faculty members who are attending this workshop are interested in developing some solutions for this kind of qubit representation, you can take up the research works here. And readable qubit for public use. These qubits are little bit unreadable format, so they are not easily readable. And if they are into public, if these qubits are going to be used publicly, then obviously there is a need for readable formats. The researchers are working on that. And again, if you are very interested in quantum computing, you can develop some readable qubit formats so that even a layman people or even a normal user can easily read quantum bits. And another challenge is that creating a scalable physical system that can support the qubit number. For example, if we have 0.000001 and 1.000 something, and again, accommodating all these huge number of qubit values is little bit difficult. And we have to create a scalable physical system. If I'm going to store 100 millions of values, these kinds of qubits, storage structure, the data structure or database schema, or if I'm going to store that in an unstructured format, how can I store? What kind of data structure or what kind of database can be created for that? So what kind of hard disk or what kind of storage device can be created for storing that? And we cannot store these quantum qubits in normal or traditional storage devices. We need to develop something else. So we can take up some research also, and that kind of physical systems should also be scalable. Scalable in the sense you all know. So today it should accommodate 50 TB of data. Tomorrow there will be a need for 1 million TB of data, means that should also be possible. Scalable physical system capable of storing so many high number of qubits should also be possible. And developing quantum gates that operate faster than decoherence time. And there will be so many gates. These logic gates will be available in quantum processing, and the development of quantum gates is again a difficult task. It's again a great challenge confronting researchers, and we can work on that. So which are very faster quantum gates we have to develop. We have to concentrate. Researchers are working on that, and we have to develop more solutions in this particular aspect. And creating spare parts that can handle the job. If you are having a quantum computer, obviously there will be so many microchips, nanochips, processors, microprocessors involved in that particular quantum computer. And if there is a failure in hardware, if a particular chip has not worked properly, so what can we do? If a particular single chip has gone through a failure, obviously the entire thing may go wrong. The entire operation may be stuck up. So I have to arrange for a spare part. So I have to arrange for an alternate option that can handle the job at that particular time. When that's a highly critical job, for example, share market, you cannot stop the share market. If there is a hardware failure in the server, you cannot stop the entire share market. So you have to find out some alternative mechanism. In quantum computers also, spare parts which are capable of handling these kinds of failures should be prepared. And will this be true? So will quantum computers be more efficient? Can this be efficiently implemented in our real world? So there are millions of research going on in this field, and with a 100 qubit computer, you can represent all atoms in the universe. Imagine a situation where how many atoms will be there in the universe, and with just 100 qubit computer, you can represent you can store all the atoms in the universe. This will be possible or not? So we have to think of. So this is not a simple task, but if research works are going on in this phase, definitely this can be possible. We do not know whether this is possible or not, but this may be possible with proper directions of research in quantum computing. So this is just a small imagination where Alice, oh Alice, you are the one for me, and but Alice is saying, but Bob, in a quantum world, how can we be sure? Because you do not know what is sure. You are now here. You are there for me. But in the next second or next millisecond, will you be there for me? Will you be existing? Will you be there? No. So you may not know where you will be there in the next second, or what will be there in the next second, or what will happen in the next second in universe. Nothing is sure. Everything is dynamically changing. In such kind of rapidly changing dynamic scenarios, definitely only quantum computing can save us. So otherwise, with the invent of new digital techniques and all those things, we will find it very difficult to digitalize everything. And without digitalization, nothing can be done in this today's scenarios, right? And Sundar Pichai, Google's CEO, he once told that I think AI can accelerate quantum computing and quantum computing can accelerate AI. So quantum computing alone cannot survive individually. So AI can accelerate quantum computing. That means to perform some quantum computing tasks, AI algorithms can be used. Machine learning algorithms can be used, or deep learning algorithms can be used. The quantum computing, that fast computation and fast processing can be done with the help of AI algorithms. That means optimization algorithms or any algorithms. And suppose if I want to if I want to make my AI algorithm or machine learning algorithm run so fast with less response time, there is a need of quantum computers or quantum computing algorithms. They go both hand in hand. Without quantum computing, AI cannot work. And without AI, quantum computing cannot work. This will be the scenario. Obviously, this scenario has come into existence and it is evolving day by day. And definitely in near future, quantum computing will rule our entire IT scenario. That's what people are expecting, and people are working towards that objective. And with this workshop, so you have 2 weeks of workshop with so many quantum computing experts delivering lectures to you, and you will have a good experience on all those things. At the end of your workshop, definitely I hope you will have new insights of quantum computing, and you will definitely start up some quantum computing research as well. And these are some of the references where you can get materials for quantum computers. And this is not the end, this is just the beginning. Thank you. So I think I have given up some idea about different kinds of applications of quantum computers, and I hope it will be useful for you, ma'am. Yes.
Yes, ma'am. Any queries from the participants, please? Write down your queries in the chat box. Thank you, ma'am.
Ma'am, really, I would like to appreciate that you have covered so many applications, and from all the domains, the people in our field, in the computer science engineering field, people are working. So these like everybody must have been able to get a glimpse of what kind of applications they can apply these quantum computing techniques. It was really a wonderful session. Thank you.
Yes, ma'am. Thank you. I must thank you for giving me the opportunity to handle the session for on quantum computing. So even though within this 1.5 hours, I may not be able to explain more applications, but I think I have given a short overview or glimpse of applications in all different domains. So
yes, ma'am. Yeah, definitely.
The participants can take up research works in any of the application which you feel is beneficial or which is of interest to you. And if you have any queries related to quantum computing, you can just post a mail. Thank you for the opportunity. Thank you, ma'am. Thank you all.
Yeah. It was an excellent session, ma'am.
Thank you, ma'am. Thank you so much.
Thank you so much.
So that is the end of the second day. today. So we will be starting with a new day tomorrow, with the day 3rd, and we will be assembling at 10 o'clock tomorrow, 10 a.m. So tomorrow session will start at 10. So thank you for having patience. Okay.
Payal, please stop recording.